We will continue our discussion on the various topics of biophotonics, and as per the module number 5 here, we are discussing lasers for biophotonics. As you can see, my pointer therefore is also the laser pointer, and today we are going to discuss a very interesting but bizarre and truly in the sense weird topic of nonlinear optical processes. Let us discuss what this nonlinearity is and how does this help us, or this pertains to the domain of biophotonics per se. Let us continue. So, as we all know that conjugate molecules, biomolecules or molecules which make biological matter are quite complicated in nature, right. Conjugated molecules are quite complicated and they have this non-homogeneous or rather heterogeneous division or heterogeneous distribution of enveloped electron cloud around it. The conjugate molecules, the biomolecules are made up of a plethora of different elements, substantial number of them being carbon, hydrogen, oxygen and nitrogen, that is the organic compounds. But as we have seen in case of proteins like hemoglobin or similar things, other higher atomic number elements can also come in. For example, hemoglobin contains iron, hemoglobin may contain iron. Therefore, the distribution of the electron cloud, so these are the schematic representation of one such conjugated molecule, and these are the distribution of the electron cloud. They around it forms a non-homogeneous, non-uniform, rather heterogeneous cloud, a heterogeneous distribution of electrons, heterogeneous distribution of electron cloud around this system, around the entire molecule. And then you know that these molecules go on being attached with other molecules by non-covalent weak forces such as hydrogen bonds and van der Waals. So, throughout the system, throughout the biological matter, throughout that biological material, there is a, I cannot state that enough, there is a non-uniform distribution of electron cloud. Now, when we subject this electron cloud, this uneven, ununiform, heterogeneous, weird in that sense electron cloud to something as intense as a laser light, as intense as a laser light. This is obviously not to scale. These are laser lights and this is much larger in size, but you use your imagination, this will be several thousand million times smaller, this entire size, and this will be larger. But nevertheless, if we subject these electron clouds which are surrounding the molecule to intense laser beams, intense laser light with specific frequencies, specific phases, specific energy values, we see somewhat of a redistribution of the electron cloud around the overall molecule. Now, let me repeat it. First, the electron cloud is uneven, the electron cloud is heterogeneous, and then we are subjecting it to intense optical light sources, i.e. laser beams, which has intense coherence, intense intensity, intense energy, phase, velocity, all of those things are there, and they, upon subjecting to this kind of a complicated and uneven electron cloud, further modifies or further bizarrely, further ununiformly, or I would use the term here, non-linearly distributes the electron cloud into the system. I told you what does linearity versus non-linearity means. Linearity is direct. X is directly proportional to y, or x is indirectly proportional to y. So, you have a very simple relationship between input and output. Non-linearity on the other hand is a very complicated relationship where there is no direct such thing. There is no direct relationship between input and output. So, we understand that the presence of the laser beam overall redirects or redistributes or remodifies this already existing uneven electron cloud, but there is not a very simple relationship, there is not a very direct relationship between one with respect to other. The overall mechanism, what happens because of this intense light beam working on top of electron cloud, the redistribution of electron cloud results in setting up a virtual energy state or virtual quantum states. What are they, you ask? Wait, I will let you know. So, what exactly is mechanism of nonlinearity? So, in bulk polarization medium, a normal material, you have the polarization given by this particular formula. The polarization of the material, i.e. distribution or susceptibility, or how the material will change, will modify in the presence of a strong electric field, is given by this particular formula, where x, well, chi actually is the linear optical susceptibility. Susceptible, I have used the term susceptible, medical doctors use the term susceptible. Some people are more susceptible to dangerous diseases than us, some people are more susceptible to bad advice than us. Susceptible is someone who are how to say it, quickly comes under the influence, So, certain materials according to the electric field quickly redistributes its electron, cloud, and how quickly, or the measure of that redistribution is given by chi. We use the term chi as linear optical susceptibility, and overall how quickly, how intensely, how much you get a dipole moment forming, how much is your electron getting modified very easily in a linear moment, in a linear material, is given by this thing, where P is the polarization, chi and E are the electric field, and chi is the linear optical susceptibility. But when you have a non-uniform material, a non-uniform or something called an anisotropic material, especially optically anisotropic material, where there are different, not a uniform distribution. Remember, biological materials are hardly crystalline like your semiconductor structures. We cannot just use this particular formula, but we have to use this particular formula and expand it as a power series, where chi 1, chi 2 and chi 3, you can consider them as power, these things starts coming into effect, where chi 2 and chi 3 especially, and this goes on forever, means because it is an infinite series, although the acceptability of chi 4, chi 5, chi 10, chi 100, chi n becomes more and more weak. But the point that I am making is, for a material where the electron distribution is non-uniform in x, y and z direction, we get this formula expanded onto some kind of a power series, where chi 2 and chi 3 are coming into effect. What are chi 2 and chi 3? These are second and third order nonlinear optical susceptibilities. These are second and third order, 2 for second and 3 for third nonlinear optical susceptibilities, and chi 2 is given by this formula, where you can understand or where you can read what the different terms of the formula mean. Now, what exactly, from a point of a layman terms, what exactly does that mean? What exactly does that mean? It simply means that when you have a system such as this with non-uniform distribution of electron cloud, different electron cloud attached to their parent nucleus differently. Obviously, when you have hydrogen, the electron cloud or electron, just one electron enveloping it, will have a different force of attraction than when you have an electron cloud enveloping iron and everything in between. I am giving two extreme cases. One have sigma bonding, one have pi bonding, one have different bonding. So, there are different forces of attraction between different electrons or different electron clouds subjected to their respective parent atom, which then form the overall complicated molecular structure. Meaning, then we cannot use the original formula P is equal to chi E, stating that the distribution of the distribution of the electron cloud upon application of an electric field is going to be uniform, right. The electron cloud around the system is itself at the beginning non-uniform. So, when you have a single light coming up, when you have a photon coming up with specific energy, specific electric field, specific magnetic field, the redistribution of the electron cloud is also going to be non-uniform. It started non-uniformly, it is going to be more, at least the chaos or the non-uniformity will increase, right. So, the formula will obviously change from a simple formula to a power series, where you start seeing higher order, second or third order susceptible terms, second and third order optical susceptibility chi 2 and chi 3 coming up, where chi 2 is given by this particular formula, where f is the field correction factor, which determines, field correction factor simply determines the electric field redistribution, electric field modification at each single atom or each single molecule per se, depending on the individual electron cloud distribution. N is the number of number density of molecules, how many are they, and beta is of course the nonlinear optical coefficient. Nonlinear optical coefficient, there are several coefficients coming up, and the beta is different in different direction, beta is different in different conditions, etc. Moral of the story, if the distribution of the electron is non-uniform in x, y and z direction, what we in optics called anisotropy, right, the electrical property or the optical property in x, y and z direction is also going to be different. I told you that at the end of the day refractive index depends on epsilon and mu, but at the end of the day both refractive index, epsilon and mu are vector quantities, right. So, if the electric field is different in different direction because the molecule is arranged differently in different direction, then obviously when you are subjecting the entire molecule to one set of electro-optic field, the distribution is also going to be non-uniform. Now, that is the closest way in which I can understand, make you understand nonlinearity. Nonlinearity means uneven or non-linear indirect redistribution of the electron cloud around a molecule which is already, which started with a non-uniform distribution to begin with, as the previous structure say. But then since it is a technology based course, so what? Okay, nonlinearity has happened, you have bizarre distribution of the electron cloud around, so what? Well, several weird things starts happening when you have a nonlinear material. When you have a material which is anisotropic, which is complex, which is differently complex in different direction, and you are subjecting it to one single type of photon or one single type of laser light, you start seeing this development of second order nonlinear optical processes becoming more and more prominent. The second order nonlinear optical processes, the most famous one of it being the second harmonic generation, SGH. In any optical lecture these days you will see people talking about second harmonic generation, second harmonic generation. What does second harmonic generation mean? Second harmonic generation distributes the energy level into real and virtual states. Previously there were energy levels, lower level, upper level, ground state, higher states, and electron absorbs light, goes from ground state or goes from lower level to upper level. After some time spontaneous emission returns back. And I have told you that the energy level are quantized, So, this level, there is nothing in between, electron cannot exist in between. Electronics engineer students knows electron can only exist in valence band or conduction band. No electron can exist in the band gap, right. No electron can exist, this is not a continuous process, these are discrete process. The very first lecture E1, E2, E3, E4, there is no such thing as E1.2 or E1.25. Well, it seems that I have lied to you, because nonlinearity falls on its face and tells you that whatever that has whatever we have sworn on, whatever we have said that this is the whole truth, nothing but the truth, turns out to be not that much truth. Yeah, I know. Welcome to the world of quantum mechanics, where nothing makes sense, where everything you can say certainty becomes uncertain. Meaning, in nonlinear optical processes, it is quite possible for two photons of same energy, E nu and E nu, that is h nu and h nu, combining together to form 2 h nu. I call them the op-amps, the operational amplifiers of optics, where one photon goes towards a virtual energy state I dash, the another photon goes to another level. This level, this energy level should not exist. This energy level should not exist. There should not be any energy level between two existing real energy state. It should not, because if it comes, it violates the Heisenberg's uncertainty principle. But guess what? It is there, and what are you going to do about it? You are, or if you think you are confused, trust me, we all are victims of quantum physics. We all are victims of quantum physics, where it does not make sense. You cannot pinpoint why this is happening, no matter what anybody says. And trust me, I have to teach this to you. Does that make it any easier for me? Thus far, I have told you that electron only will be absorbing a particular frequency of photon, and if that frequency matches that of the band gap, it will go upstairs, and then after some time, etc., you know the whole detail. But now I am asking you, now I am telling you that electron can also absorb half an energy of that photon or a wrong energy of photon, and can go only half, where it can create its own virtual energy state. Right? An imaginary energy state, virtual energy state or virtual quantum state. What does that mean? That means they are unobservable states. We are only able to understand their presence by theoretical and mathematical calculation. Our experimental results fail. Our experimental results thus far has failed to observe it. We do not define it by some kind of an eigenfactor. These exist, and without bringing them into our equation, we will not be able to demonstrate, or we will not be able to explain what is happening here. This is an experimental phenomenon. Where you have sent two beams of the exact same frequency, same phase, same velocity, and you are seeing the output is a combination of nu 1 and nu 2. A combination. This is like your adder in op-amp. If you have nu 1 and nu 2 equal to nu, as in this case, you have 2 nu in the output. That is the second harmonic generation. You send two photons of the same frequency, you get the output as a sum, as an addition of these two. And how does that happen? We have come to this explanation. That the electron, because of the presence of the photon, because of the presence of the intense beam of the light, this is the complex material, this is the this is the complex conjugate molecule, this is the anisotropic material, this material has ununiform distribution of photon around it. So, the ununiform distribution of electron around it. And because of the presence of this photon, the electrons are again redistributed in a far more chaotic manner. The chaotic manner is creating virtual states, imaginary states. Just let that sink in. Now, what does imaginary energy state means? It does not mean like Harry Potter or Superman, Batman or Star Wars, anything like that. Electrical or electronics engineer students knows that when we talk about the resistance coming from capacitor or inductor, we use the term I, root over minus 1, that is the imaginary term. What does that physically means? Does it physically means that capacitor or inductor's resistance to the flow of current is imaginary, do they not actually prevents the flow of current or resist the flow of current through them? How do you define in that particular case? I would like that you utilize the same imagination to explain the imaginary term here, because imaginary state should not exist. Imaginary energy state should not exist. They violate the every other fundamental principles by which quantum physicists swore their name on. This is what we are. We are quantum physicists, and Heisenberg uncertainty principle, what governs us? Well, Heisenberg's uncertainty principle is not followed here. What are you going to do? But you do not have any better explanation. You do not have any better explanation, and this is the only explanation, plausible explanation, that we can come up with to describe the actual phenomenon, that why, oh why, that when we send 2 photons, we get the output as a sum of the energy, sum of the frequency of the 2 input photons. Suspend disbelief. I do not know how you are going to cope with it. I am still grasping with it, and I will let you know a secret. All of us are. This is quantum physics. One single photon can pass through 2 different slits at the same time. So can be an electron. We can have virtual energy states happening where the electron will absorb the wrong photon. The electron will absorb the wrong photon, go somewhere else, then absorb another photon, go somewhere else, and then return back, giving rise to one single photon, which combines the energy of these 2 photons. Right? A virtual energy state has come, and we have not been able to describe it, or we have not been able to observe it experimentally. There is virtual state spectroscopy coming up, and several new work is being done, but we are still, this is a very short lived state. The idea is that it takes some time for Heisenberg's uncertainty principle to kick in. Before it kicks in, this electron has moved, or this electron has gone back. This is somewhat of a hand waving idea that describes the overall nonlinearity process. And how do you differentiate a virtual state from a natural state, virtual state from an already existing state? It's easy in fluorescence. In fluorescence, we have a broad distribution. Remember those emission and absorption curve, they have several broad distribution, they randomly distributes. Here, it is a very, very sharp spike. This is a very, very sharp spike in which the electron, which occupies a virtual energy state, occupies it for a very, very small instance. So much so that despite our attosecond cameras, femtosecond cameras, we are still unable to capture it. Is it true, you ask? Is this explanation, incomplete explanation, is it true enough? I do not know. I am not a quantum physicist, but this is the best explanation we have thus far. This is the best explanation we have thus far, and we have utilized. What is the explanation? That because of the presence of intense light beam, the electrons redistributes, the electron cloud redistributes. Since there are different electron clouds, they have their own repulsion and attraction among each other because of the different types of atoms that forms this entire material. They create virtual energy states, and they will behave non-linearly, they will behave in a bizarre manner, indirect manner, weird manner. And when you give 2 beams of photons of the same energy, same velocity, same phase, we see output coming up. And this part is experimentally observable. We saw this experimentally happening, and then we tried to explain it mathematically, and therefore we got into trouble, and thereby we started setting up of virtual energy state. Well, virtual energy state have previously been discussed before nonlinear optical process were coming in, but you can understand that it was not very popular at that time. But when nonlinear optical processes were experimentally observed, we have to invoke virtual energy states, otherwise it will never get explained. And we see this happening every day in our laboratories, where some kind of a nonlinear crystal, for example lithium niobate, these complicated crystals, they have different arrangement in different direction. When subjected to beams of light omega 1, several sources of omega 1, it generates 2 omega 1 and omega 1 at the output. This 2 omega 1 is a combination of omega 1 plus omega 1. This is not exactly a right picture, this is actually fluorescence, but you can understand that we have been able to measure, we have been able to calculate, we have been able to observe this phenomenon throughout in our experimental results, throughout in our laboratories. When we try to explain nonlinearity, we invoke virtual quantum states. Virtual quantum states and virtual quantum states obviously bypasses or breaks several existing quantum mechanics rules. What can you do? You tell me, come up with a better explanation. I ask you, come up with a better explanation. Thus far, this is the best explanation we have. Yes, I know how incomplete it sounds, but this is the best explanation we have. You can knock yourself out with as many mathematical derivations as you want, but at the end of the day, it still boils down to the fact that virtual energy states make zero sense. Virtual energy states make zero sense, and yes, energy state splitting, this, that, everything is there. But explain me, any physicist, I am asking you, explain me the virtual energy states in a proper manner which does not violate the previous principles that we have discussed. So, where we use them? Again, the so what question? Well, a very easy thing is we use it for lasers. We use it to create or tune lasers. Think about it, omega 1 may be the wavelength of light of a laser light at red. 2 of the red wavelength light, say around 800 or 750 or 700, combines together and gives you an output laser which is twice that of the frequency, and thereby you can convert or you can tune a low frequency laser into a high frequency laser. You can tune a low wavelength laser into a high wavelength laser. Also, there are certain conditions that needs to be fulfilled to have this second order harmonic generation. It does not happen to any material. I told you it has to be anisotropic. It has to be, as they use the term, it's a better term, non-centrosymmetric. You have to have chi 2 is not equal to 0 and beta is not equal to 0. Several materials have these things 0. You do not see this bizarre thing happening in any material. I told you this happens in conjugated materials, but there are far more conditions that the molecules have to be non-centrosymmetric. This is a better term. What does that mean? Meaning it is not symmetric across its center. Consider the benzene molecule. You remember that benzene molecule is like that. It's like that. If you slice it into half, you get equal half. You get equal half. This is a superposition principle, that inversion symmetry. If you invert it, they are symmetrical to one another. If you invert it, it is symmetrical to one another. Consider the benzene molecule. It is symmetric across its center. However, if the molecule needs to show second order processes, it needs to be non-centrosymmetric, i.e. the molecule in bulk also are arranged in non-centrosymmetric structure. It should not be that the molecule is non-centrosymmetric just by itself in the molecule. The arrangement has to be non-centrosymmetric as well. Now, here please mark my word, non-centrosymmetric does not mean random. It does not mean random, it simply means asymmetric. These are two separate words. Random arrangement is different. Random arrangement, you take some amount of marbles, throw it away, and this is a random arrangement. Non-centrosymmetric is deliberately making it so that it is not symmetric in x, y and z direction, and you cannot get this randomly, because in random process some of them might be similar, some of them somewhere might be similar. Non-centrosymmetric ascertains that it is not symmetric across its center, meaning an example is 4-nitroaniline. This is a stick figure of 4-nitroaniline. You have NO2 at one hand and NH2 at one hand. This is the amine group. Amine, ammonia, the strong smell you get when you enter a lavatory or a laboratory, ammonia. NO2 is the nitrogen dioxide, and no matter how across the center, if you cut it like this, or if you are having difficulty cut it in this particular form, you will see that it is asymmetric molecule. There is a different arrangement here, there is a different arrangement here, and if you cut it through this, you will see asymmetry or non-centrosymmetry in one particular direction. There are other molecules, for example, I do not know, lithium niobate is probably asymmetric in Z direction, it is not symmetric in X and Y direction. So, that matters, but there are several complicated molecules, DNA for example, which is, correct me if I am wrong, which is non-centrosymmetric. I might be wrong, just check into it, but you get the point. You get the point that this has to have an asymmetry around it. These are not randomly arranged, obviously not. These are not randomly arranged, and when they combine together with other molecules, they are also not randomly arranged, but the fact of matter remains that they are non-centrosymmetric, meaning the electron cloud enveloping them is also non-centrosymmetric, and when they are subjected to intense light beam, like consider my pointer to be a light beam, they get redistributed. The redistribution, the remodification creates virtual energy states. The virtual energy states give rise to all these bizarre things that comes up. Not every biological material has non-centrosymmetricity. Not every biological or conjugate material has it. However, several of this nitroaniline, certain proteins, etc., does have it. A primary example of where we can utilize it is your second harmonic imaging microscopy. So, you have a material, collagen for example, is a non-centrosymmetric biological protein. Well, collagen, well, yes, it is kind of a protein, and you know what collagen is, for you have thus far gone through all the courses. Suppose we want to look into how the collagen is distributed inside the tissue. We put it under a microscope slide, we put it under a slide, in a slide, put it under a microscope, and the microscope gives two strong beam of light. That beam of light, when encountering the collagen, because of the nonlinearity process, gets either reflected or transmitted, combine effect, a 2 omega effect, omega 1 omega plus omega gives rise to 2 omega, and if you have sufficient filters, sufficient light filters, which can only filter out the 2 omega part in a plethora of tissues, say for example, this is looking at the collagen distribution in liver, rest of the areas are not non-centrosymmetric, they are centrosymmetric, or they are not producing the nonlinear effect, thereby they will not emit 2 omega when they are subjected to omega plus omega. They will not emit 2 omega when they are subjected to beams of omega. They will not emit photon of double the frequencies when they are subjected to single photon frequencies. They will behave normally. You can therefore identify and locate how the collagen is distributed, and if you can identify or locate how the collagen is distributed, you can take some make some inference, make some analysis. At the same time, if you see some kind of a disease happening, if you see some sort of a disease taking place where the collagen is breaking down or the collagen has some sort of a problem, you might think that the molecule is undergoing some sort of a change. If the molecule is undergoing some sort of a change, if a pathogen has attacked, if a foreign molecule has come up, something else have happened, maybe the nonlinearity will be disturbed. If the nonlinearity will be disturbed, 2 omega will not be emitted back. If 2 omega is not emitted back, you will see black patches. So, you compare like with like, and you come to a conclusion that this part is probably not all right. So, conventional optical microscope deals with optical density, refractive index, path length. The second harmonic microscope only depends on the generation of second harmonic light. Second harmonic light, omega plus omega, 2 omega. If 2 omega is returning back, you have sent 2 two red lights only when you see blue light returning back or green light returning back from a particular specific area. You know this area is collagen because collagen is the only nonlinear material there, and this is the distribution of the collagen, and from the distribution of the collagen you are diagnostics whether the distribution is right or wrong, whether there has been some kind of a problem with the distribution, etc. We also see third harmonic generation. Yeah, I know it is 4-wave mixing where you know photon 1, photon 2, photon 3 combines, and you give, instead of 2 omega you give 3 omega. Yeah, I know. Will you be mad if I say even the top one is also virtual state? Yeah. Don't hate the messenger, as they say. Don't shoot the messenger, as they say. I am simply the messenger. Remember, Schrodinger said that I am sorry I have anything to do with quantum physics. I have not developed quantum physics, not at all, heavens forbid, but I have to teach, and I am already apologizing. So, those of you who want to go into this direction, you know what you have to tread with. So, third harmonic generation, the more you go further, the more bizarre it happens. One saving grace is that these things are in relatively few compounds, not in a everyday compounds, can be considered as Chi3 or Chi2. Well, depends what you use in an everyday basis. Silicon shows Chi3, so semiconductor physicists can talk about Chi3, but the further it goes Chi3, Chi4, it becomes weaker, the effect becomes prominently weaker. But nowadays we are utilizing different types of laser beam to enhance Chi2, Chi3 effect. For Chi3 you don't even require a symmetry restriction, can happen in any medium, so no one is safe. And multiphoton absorption, read a bit about multiphoton absorption. This is related to the Raman scattering. Multiphoton absorption we use in several different, so this is multiphoton absorption. 3 different types of photons are getting absorbed, and the emission is a combination of all 3, giving rise to bizarre things happening. So, this is thus far the topics that we covered for today. Nonlinear optical processes, second harmonic generation and the third harmonic generation. I did not discuss too much of third harmonic generation because it will take us into the deepest and the darkest side of the woods. Let us stick to second harmonic microscopy. It is a special kind of microscopy that is specific to our biophotonics. Biophotonics is also utilizing third harmonic generation 4-wave mixing, which is Raman scattering. And if you are more interested onto knowing nonlinearity, this bizarreness in quantum physics, try reading photonics part, chapter number 4 or chapter number 5 by Ralph Menzel, very good book. Try to see if you can get it from a library, and of course the other books are our constant companion. So, thank you. I hope you survive this. Thank you very much.